The working principle of transformer. Actually, transformer is a machine, but it does not have any moving part. That is why a transformer is referred to as a static machine. A transformer has three main parts, two windings, and a metallic core on which the windings are wound. Windings are in the form of coil made of a good conductor of current. The windings of a transformer play a main role in the machine. The winding coils behave as an inductor. When an alternating current is allowed to flow through any of the windings, there will be an alternating flux produced surrounding the winding. The magnitude of this flux is proportional to the magnitude of the current flowing through the winding. The direction of the flux is according to the direction of current. The direction of the current in the winding can be found out by applying right hand grip rule. This rule states that when we grip our right hand with stretching the thumb along the axis of coil or winding and other forefingers along the direction of current in the coil, then the thumb indicates the direction of produced flux inside the coil along the axis. This flux becomes maximum in magnitude when current reaches its maximum for 1/2 cycle of the alternating current wave. The flux becomes zero when current in the coil crosses zero axis. Again, for next half cycle, the flux becomes maximum but in opposite direction when current reaches to its reverse maximum. In this way, alternating current produces continually varying flux surrounding the winding. The flux lines link the winding itself, and the flux is varying, so there will be self-induced EMF across the winding. This phenomenon is due to Faraday's laws of electromagnetic induction. This induced EMF or voltage, whatever you say, is same in magnitude and opposite in polarity of supply voltage. Supplied alternating voltage causes alternating current in the winding, which produces continually varying flux inside and outside the winding. This continually varying flux produces induced EMF across the winding. So we can say that the supply voltage is caused, and induced voltage in the winding is an effect of this cause. Hence, according to Lenz's law, this induced voltage will be in opposite polarity of supply voltage. Since, according to Lenz's law, effect always opposes cause. This self-induced voltage across the winding does not depend upon the number of turns in the winding, but depends on the supply voltage. But the voltage induced per turn depends on the number of turns in the winding. This is nothing but induced EMF divided by the number of turns in the winding. We have said that there is another winding in the most basic transformer, but till now we have not discussed it. Now we are coming to second winding in the transformer. Supposing one separate winding is brought nearer to the first winding, then this second winding gets kinked with a portion of varying flux of first winding. Due to this varying flux linkage, there will also be an induced EMF across it. This induced EMF would be quite small, as because the flux linkages is small. Hence, rate of change of flux linkage is also small, and according to Faraday's laws, induced EMF across a coil is directly proportional to the rate of change of flux linkage. If now we connect a closed circuit across the second winding, we will get a very tiny current through the circuit, provided the second winding is placed much nearer to the first. So we have seen that some portion of the input power is transformed to output through the second winding. This is because some portion of generated flux of first winding is linked with second. Now, if we want to transform maximum electric power from first winding to second winding, we have to link maximum flux of first winding to second winding. This is done by placing a low reluctant magnetic core in between these windings. Steel is a well-known low reluctant magnetic material, so we normally use steel for making low reluctant magnetic core in the transformer. As soon as we place a steel core in between these windings, nearly the entire flux which was surrounding the first winding will be concentrated inside the core and linked with the second winding. As nearly the same flux links with second winding, now the rate of change of flux with respect to time is equal in both windings. Since as per Faraday's laws of electromagnetic induction, induced EMF across a conductor is directly proportional to the rate of change of flux linkage. The voltage induced per turn in both windings will be the same. We have already explained that voltage induced across the first winding is the same as the supply voltage. Actually, here we consider that there is no voltage drop between supply terminals and the first winding. This is an ideal case. For theoretical purposes, we will consider that condition. As this first winding is connected with supply, it is referred to as primary winding. Now, if this primary winding has N1 number of turns and supply voltage or induced voltage across primary winding is V1, then voltage per turn in the primary winding is V1 by N1. So far, we have understood that exactly this V1 by N1 voltage will appear across each turn of second winding. So if this second winding has N2 number of turns, then total voltage across the second winding is N2 into V1 by N1, and let us say this is V2. If now any closed circuit is connected across the second winding, it will provide voltage V2 across the circuit, and due to the voltage there will be current flowing through the circuit. Normally in a transformer, this second winding is connected with load circuit. This winding is referred to as secondary winding. If the number of turns of secondary winding is not equal to that of primary winding, that is, if N2 is not equal to N1, then secondary voltage of the transformer is different from primary voltage. Now if N2 is greater than N1, the secondary voltage will be more than primary voltage. On the other hand, if N2 is less than N1, the secondary voltage is less than the primary voltage. The former is called a step-up transformer, and the latter is called a step-down transformer. This is the most basic theory of a transformer. Hope you understand.